Hi everyone, my name is Noor and I am a PhD student at the University of British Columbia in Canada. I am very honored to present my recent work, BiasPruner, and I hope you find it as exciting as I do. Now let's imagine a doctor learning to diagnose diseases but forgetting previous conditions every time a new one is introduced. In deep learning, this is called catastrophic forgetting, and it happens when a neural network forgets the knowledge it has learned before when it learns a new data. And this is especially critical in the medical field, where the networks need to adapt to new diseases, demographics, from new devices or hospitals without sacrificing what they already know. To overcome catastrophic forgetting, we use continual learning. Continual learning allows deep networks to learn new tasks or data sequentially over time without forgetting the old ones. And by the end of each learning step, the network can perform well on all the tasks it has learned so far. There are different techniques used in continual learning. Replay-based methods store and replay old data to help the network to remember, but this is not so practical in the medical field due to data privacy issues. The regularization-based techniques penalize the network updates that would alter the important previous knowledge. And the architecture-based methods, specifically the subnetworks, dedicate specific parts of the network to each task to avoid the knowledge interference. However, most of these existing continual learning methods only focus on minimizing forgetting. But here is the real question. Is catastrophic forgetting the only challenge we face in the medical field? The answer is no. And here's the catch. While those continual learning methods reduce forgetting, they do not tackle the bias problem present in most, if not all, the medical datasets. The bias occurs when the data used to train the network does not represent the actual population. So it might be skewed towards a specific gender, like a skin tone or age. Or it could come from image artifacts that appear in some devices but not the others. All these factors lead the model to learn spurious features that are not medically relevant, and we call this shortcut learning. Now let's go back to our network. Imagine we wanted to learn in a continual manner. If we have not considered the bias from the start, things get even more complicated. Why? Because if the dataset is biased, the bias it picks up early on gets transferred to the new task. So even if the future data is perfectly unbiased, the bias that the network has learned before will affect learning the new task. And this is due to the bias transfer problem. And this is going to make the network unfair. Now let's pause for a second and let's imagine the disastrous scenario when we have a long sequence of tasks to learn. And here comes our motivation. What if we thought about forgetting differently? So instead of always asking, how can we stop forgetting? Let's ask, can we use forgetting to our advantage? What if we could intentionally forget the shortcuts in the network? So those spurious correlations that lead to unfair model. In this case, forgetting could actually help improve fairness by removing the parts of the model that are responsible for biased decisions. And here comes our BiasPruner. BiasPruner is a continual learning method that leverages forgetting to improve fairness while still ensuring the model does not forget the important things it has learned. So now we have introduced the challenges of catastrophic forgetting and bias. Let's remind ourselves of the goal of BiasPruner. So here the goal is to tackle both problems simultaneously. So enabling the continual learning without forgetting the important information while also mitigating the bias that sneaks into models during training. Now let's take a look at an example where we have a network learning from task 1 dataset. In this dataset, we have two target classes, each with an imbalanced number of males and females. With the BiasPruner, it's going to learn the classification task by pruning away the biased parts of the model, and the result would be a task-specific subnetwork that is debiased and that is only dedicated for the task. How does BiasPruner form debiased subnetworks? As I mentioned earlier, we're going to prune the network units based on their bias scores. And for this, we propose the bias score as a measure of the contribution of each unit in the network to learning spurious correlations. Let's find out how to measure the bias score. First, given a biased dataset, one of the key causes of learning shortcut predictions occurs when the model finds it easier to learn the spurious features rather than the intended ones. So consequently, we propose to intentionally encourage the network to quickly fit on the easier images from the training data using this generalized cross-entropy loss. So by looking at this loss or the gradients of the loss, it actually upweights samples with a high probability of predicting the correct target, and therefore, by the end of the training, our network will become biased. Once the network is biased, we are going to partition the training images into easy and hard samples. Now, the easy samples are those that the network was able to classify correctly with a high confidence, whereas the hard samples are those that were misclassified. Finally, we're going to use the ReLU activations. So basically, we're going to calculate the variance of each unit's response to these samples, and that would give us the bias score. So the units that respond more strongly to easy samples are assigned higher bias scores, while those responding to harder samples receive lower scores. Once we have all the bias scores for all the units, we're going to prune the units with the high bias scores, and that would give us the subnetwork. Finally, we fine-tune the subnetwork using a weighted cross-entropy loss, where easy samples are down-weighted, whereas the hard samples are up-weighted exponentially, and this would give us the debiased subnetwork. We evaluate BiasPruner using three different datasets where each one has a different bias or sensitive attribute that is strongly correlated with the disease class. And we adopt a class incremental learning setup where classes in each dataset are split among the different tasks. So for example, the Fitzpatrick, we have 114 classes and we formed 6 tasks. So we have 19 classes in each task. And to evaluate BiasPruner, we use the F1 score, the overall accuracy, and the accuracy per sensitive attribute. And for fairness measures, we use the DPR and EOD. Now, for the three datasets, we compare the performance of BiasPruner with the three baselines and the three continual learning methods. And to provide a better comparison, we also incorporate bias mitigation techniques into existing continual learning methods. And finally, we benchmark against a recent SOTA method for bias mitigation. And the results, so here we can see that the BiasPruner significantly outperforms the others in terms of both accuracy and fairness. We also explore the decodability of the bias in frozen networks pre-trained using the cross-entropy loss, the generalized cross-entropy loss, and our BiasPruner. And we can clearly see that the bias decodability is lower in BiasPruner, indicating its effectiveness in mitigating bias. And that was the end of our presentation. Thank you so much for listening.